Have you ever wondered how your computer can juggle, a dozen different apps, 100 browser tabs, and maybe a video call all at the same time without just collapsing into a pile of digital nonsense? Well, the answer is one of the most elegant and powerful illusions in all of computer science. Today, we're going to pull back the curtain on the magic trick that makes all of modern computing possible: virtual memory.
I mean, really think about it. This is the central question, right? You've got your email client, a music app, maybe a game, all running at the same time. How do they not trip all over each other? How does your game not accidentally reach out and grab a piece of memory that belongs to your email, causing everything to crash? This is the fundamental challenge that virtual memory was created to solve.
What's kind of funny is the authors of our source material, the O-Step textbook, they humorously blame us. Our demand for a computer that can multitask seamlessly is the very thing that created this massive but, totally fascinating engineering headache.
So to really get why this solution is so brilliant, we first have to travel back in time to the early days of computing, when things were much, much simpler. Let's take a look at how the very first systems handled memory. In this early model, the simplicity is just stunning. Physical memory was literally split into two sections. That's it. You had the operating system sitting at the bottom, and then one, and only one, program got the rest of the space. What you saw was what you got. No tricks.
Now, this approach was clean, sure, but it was also incredibly inefficient. I mean, can you imagine having to shut down your word processor completely just to open a calculator? You could only do one single thing at a time, and for these super expensive machines, that was just a huge waste of resources. So yeah, obviously, that couldn't last. We started demanding more from our computers. We wanted them to be way more efficient and way more interactive, which led to a brand new era of sharing the machine.
Two key ideas really drove this change. First, multi-programming. The idea of keeping that expensive CPU busy by always having another job ready to go. And second, time sharing, which was absolutely revolutionary. It allowed multiple users to interact with one single machine at the same time, all of them feeling like they had it all to themselves.
And this brought us right back to that core technical challenge. How do you actually get multiple programs to live in the same physical memory at the same time without them, getting in each other's way?
Well, the first attempt was, frankly, a bit clumsy. The idea was you could run one program for a little bit, then save its entire memory to a slow disk, then load another program's entire memory from that disk, and just keep swapping back and forth. The source material calls this brutally non-performant. Yeah, no kidding. The much better approach, the one that won out, was figuring out a way to keep multiple programs in memory at the same time.
And this is what that better way looks like. See here, we have process A, process B, and process C all loaded into physical memory together. This is so much faster and more efficient, but it introduces a huge new danger.
And that new danger is all about protection. With all these programs sitting right next to each other in raw physical memory, what's to stop a bug in process A from accidentally writing over the critical data in process B? Or even worse, what if it corrupts the operating system itself? The entire system was now incredibly fragile.
This is where the story gets really good. Because the solution to this problem of protection and sharing wasn't just a simple fix, it was this elegant and beautiful breakthrough known as the address space.
So what is an address space? It's the core of this whole concept. It's an abstraction. It's a private, clean, perfect view of memory that the operating system gives to every single program. Each program is essentially tricked into believing it has the entire computer's memory all to itself.
And this private little world is perfectly organized. The program's instructions, its code, are placed in one area. Then you've got two flexible areas for data. The heap, for things the program creates on the fly, it grows in one direction, and the stack, which tracks function calls, it grows in the opposite direction. They grow towards each other, creating this tidy, self-contained universe for the program.
Okay, but wait a minute. This should raise a huge question. If every single program gets its own perfect address space that starts at address 0 and goes up to 16 KB, where are all these identical spaces actually located in the one real physical memory? They can't all be in the same spot.
And there it is, the big reveal. It's an illusion. That neat, tidy address space doesn't actually exist in one continuous block of physical RAM. The operating system and the computer's hardware are in a constant high-speed partnership, translating every single memory request from the program's virtual address to its real physical location. It's a sleight of hand happening billions of times per second.
Now, for this incredible magic trick to actually work,
the virtual memory system has to play by 3 really strict rules. These are its fundamental goals.
First, transparency. The program must have absolutely no idea this translation is even happening. To the program, it's completely invisible. Second, efficiency. This whole virtualization dance has to be incredibly fast, but it also has to be efficient with space. And third, and this is the big one, protection. Each process is sealed inside its own address space, completely unable to touch the memory of any other process or the OS.
And this goal of protection gives us the critical property of isolation. Each program runs in its own safe cocoon. It means that when your web browser crashes, it can't bring down your operating system with it. Isolation is the very foundation of a stable, reliable computer.
All right, let's bring this all home with the final and maybe the most mind-bending reveal of all. Because this isn't just some abstract theory. This applies to every single line of code you've ever written and every application you have ever used.
The source material just states it perfectly, with zero ambiguity. In fact, any address you can see as a programmer is a virtual address. Every single one.
And these addresses, they look so concrete, don't they? If you write a simple program and ask it, hey, where's your code? Where's your heap? Where's your stack? It'll give you these big, specific numbers. They look so real. But they're not real. They're all virtual addresses. They are simply coordinates inside that private, illusory address space we've been talking about. They are part of the magic trick. Only the operating system and the hardware know the real physical truth of where that data actually lives on your computer's RAM chips.
So, the key takeaway is this. The memory you interact with as a user, as a programmer, it's a sophisticated illusion, engineered for safety, efficiency, and ease of use. Which leaves us with a final question to just let that sink in. If every single address your program ever sees is just a piece of that illusion, what is the real truth of your computer's memory?